Welcome students to the class. So today we'll be learning about just one topic, and it is called torque. Most probably you have come up with the ideas called force in linear motion. So what actually force does, if you think about a stationary object, then if you apply force on it, by Newton's law we say that F equal to mass into acceleration. It means if you apply force on an object, then it's going to result in acceleration of this object. For example, let's take this is the object which was, let's consider initially at rest. On application of this force, it's going to accelerate in this direction. Okay. In a similar way, what is going to cause angular motion of an object? Because you see, whatever we are using as a force term, so this is what? Linear acceleration, right? Linear acceleration. So, in this class, we are going to learn about what kind of thing is going to cause angular motion or angular acceleration of an object. Alright? Okay, so first let's set the target. Let's get rid of these things, and in today's class we are going to learn about the concept of torque. Okay? I'll say, let's imagine an object. Let's imagine this is an object, and we have to move this object from this position to this another position. Okay, that means this is the amount of displacement that has happened with this object. Now here comes a question. In your day-to-day life, you can observe, or you might have observed that whenever we have to set something in motion, then we have to supply this with energy. Okay? Now, in thermodynamics, most probably you are aware of this thing, or even if you are not, then I'm telling you right now that if you have to supply energy to a system or to an object, then you can do it only in two different ways. There are only two ways. And those are, number one is work transfer, and number two is heat transfer. Work transfer and heat transfer. These are the two ways. These are the two ways we can transfer, or I would say mode of energy transfer to an object. Okay. So that means, as we have started with this question, how we can move this object from this position to that position, the basic answer is going to be, from our day-to-day life experience, is going to be transfer of energy to this body. Okay, so from this thing we have come to know that this can be done either by using work transfer or heat transfer ways. Okay, so let's focus on work transfer thing, and because with the help of this work transfer thing, we'd be able to understand the concept of torque and also the work. Okay, I'll say it. Okay, let me keep it in this side. Great. Okay, let's think about that example. That means this is an object I have applied with some kind of a force, and as a result it has moved from this position to that position. Say it's a new position. This position, and this is the amount of displacement to this object. So as I said, we are going to use this concept of work transfer. So here, to move this object from this position A to say position B, what we have done? We have done this thing. We have supplied energy to this system, or let me write it here. Energy supplied to this object. Energy supplied to the object, which is work on the object, okay, and which can be written as F vector dot displacement vector. Okay, great. Clear? Now let's do one thing. Let's bring one more concept. So let's consider that this is the concept number A. This is concept number A. Now we know that if we think about a circle, and if we consider 2 points which are very close to each other, so this is say A and this is say B. These 2 points are very close to each other. As these are very close to each other, then we can think that the separation between them is basically a straight line. Okay, a straight line. That means the separation between point A and point B is basically a straight line. Let's name this straight line as dx, its length. And if we imagine this to be a vector, then we can say that this is basically what? Dx vector. Okay, great. And you know that if we think that this circle is very, very big, then only we can say that the separation between A and B are going to be kind of a straight line. All right, let's add these 2 concepts to understand this concept of work transfer. Now say, if we imagine the center of the circle that I was talking about was right here, okay, and this is the initial position vector. This is the initial position vector. Let's say this is R I vector. That means if we think about this to be the origin, then from this origin the position of A is given by Ri vector. And the next position of the same object, this position B will be given by this Rf vector. Then from this triangle vector addition, you know that this dx vector is basically Rf vector minus Ri vector, okay, and which also can be termed as some kind of a change of position vector, and this is what? Change of position vector. Change of position vector. Okay, great. Now let's go back to this thing where we were to this thing. The energy transfer to this object. Okay, that means this thing. Let me keep it aside. All right. Okay. So, if we again draw this object at position A, and that means at this position A, that means if we imagine this object to be that object that we talked earlier, to be right here, and it was moved from this position to that position on application of this force, then we can write this equation, this equation, F is equal, work on this object is equal to F vector dot dx vector, again as this thing. So work on the object is going to be again what? F vector dot dx vector. Now see, F will remain as it is, but if you think about this triangle, then if we imagine this angle to be, d theta, then we know that d theta is equal to arc upon radius, dx upon r. And actually, if we make this d theta look like a vector, if we consider this separation, that means separation between a and b, which is also this dx thing, to be very, very small, then we can think of this d theta as a vector quantity. Okay? Then, putting this vector, so I mean to say, if we turn this thing into some vector form, then it's going to look like this: d theta vector cross r vector as dx vector. So, in place of this thing, what we can write? D theta cross r vector. Now, here we will have a vector quantity, then there's a dot product, then we will have another vector quantity, because you know that the cross product of two things results in another vector quantity. Okay, great. Now there's a rule in mathematics which we are going to use here. Now see, if you think about three vectors, A vector, B vector and C vector, and the connection between them is like something like A vector dot B vector cross C vector. Okay, so if we start here, then we multiply this thing with B and C using this dot product, then this will be also equivalent or equal to B vector dot C cross A. And also, if we start with C, then doing the dot product, we can say A cross B. Okay, A cross B. So if we imagine this to be A, this to be B, and this to be C, then you see we can also write as, using this particular concept, R vector dot, let me get rid of this extra ones. Okay, so in place of d theta, okay, see A cross B, right? A is what? F vector okay. Alright. So A dot B cross C is equal to, yes. So this is the thing. Anyway, so somehow we have to write it as this thing in this form: C vector dot A vector cross B vector. Or in the same way, we also can think about this one. So instead of this expression, let's focus on this expression, because this is going to be far more important for us. Okay, ready? Then we can write, in place of B vector, what do we have? D theta. Okay, then dot product here, it's a dot. Then in place of C, what do we have? R vector, there's a cross. And in place of A vector, what do we have? We have what? F vector. Okay, I'll see. We can flip their positions, because this is dot product, their position does not matter much. Dot d theta vector. Now interesting thing appears here. We started with a linear term, which is linear displacement. Okay, simply displacement, and we have ended up with what? Angular displacement. Okay, now see, whatever work we talked about, whatever work thing we talked about, that means work supplied to an object resulted in displacement of this object. But in doing so, what we had to apply on this object is the force. That means if we want to move an object by this amount of displacement, then we have to supply or act this body with this amount of force, so that we can supply this object with this amount of energy. Now, can we say the same thing in terms of angular motion? Now see, so if we think that instead of supplying, or instead of changing its I would say linear position, or in other words we can say, instead of giving it some linear motion, if we give it some angular motion, which is d theta, then what kind of thing we have to act this we have to act upon this body with? Okay, then this is going to be this thing, and we call this as what? Torque. Okay, so this is a symbol for torque, and thus we have come up with a symbol, or come up with a formula, and it is what? This torque vector, this is termed as torque, as what? R vector cross F vector. This is it. And if we do the calculation of this cross product, and if we try to write this I would say magnitude, then it's going to look like what? RF sine of theta. Okay, RF sine of theta. The interesting thing is, so this is a very basic formula. All right, now let's do some example based on this thing. So let's take this an object, and it is given this amount of force. This is F. Then we can think about some kind of a line of action. This is what? Line of action. Okay, and this is the point about which this movement is happening, or this object is going to move. So we consider this point to be pivot. This pivot is a point about which an object can turn. And this is the point of application of force. Let's take this is point as A, and this is going to be R vector actually in this case. All right. And what is the angle between them? Angle between them is going to be this much. This is going to be termed as theta. Okay. So if you think about this in a bit other way, or I would say if we rearrange this thing, this is going to look like R sine theta times F. And this thing, this R sine theta from this diagram, you see, is going to be, this is R. Then if you make a perpendicular, if you draw a perpendicular to this, then this is going to be R sine theta using simple geometry. Okay, so it means whatever this thing is, it is going to be perpendicular separation of this line of action. Of what? Of line of action times the force. This is going to be value of torque applied on this object. And using the cross product thing, we also can see the direction of it. That means if we think about this R vector here and F vector acting this way, R vector cross F vector is going to turn in this way. That means this is a three-dimensional figure. So if we think about the whole thing today in this two-dimensional way, that means, so this is the object, and this is the axis about which it can rotate, and this is the point pivot, and this is a black disc-like thing. It is from the side view, and we have applied the force right here. So this is going to be expressed with cross thing, and from here to there, this is what r vector. So say r vector is here and f vector is toward the board, right? So r vector cross f vector is going to rotate in this fashion, okay? Or in other words, if we think about the direction of it, using right hand thumb rule, we also can say that this will be the direction of torque. Is it clear? So that was it. So this is the way we derive the formula for torque using the concept of energy transfer. Thank you.